They told you winter heat had to come from somewhere expensive. A gas line running underground from a utility company whose rates you have no control over. A propane tank sitting in your yard that gets emptied faster than you expect and refilled at whatever price the delivery driver quotes you that week. A furnace installed by a contractor, maintained by a contractor, repaired by a contractor, with filters and sensors and circuit boards and igniter assemblies that fail reliably on the coldest night of the year when no one is available, and the repair bill comes with an emergency surcharge. They told you this was simply the cost of staying warm. That comfort in winter was something you rented month by month, degree by degree, from companies whose entire business model depends on you having no alternative. But right now, in a small workshop outside northern Sweden, a family is heating their home with nothing more than crushed stone, steel pipe, and heat. They captured weeks ago from a wood fire they burned on a Saturday afternoon. No flame burning tonight, no meter spinning somewhere in the dark, no truck scheduled for a delivery that may or may not arrive before the tank runs out. Just stored warmth, patient and quiet, slowly moving through the walls of a well-insulated room while snow piles against the windows and the temperature outside drops below what most people in warmer climates can easily imagine. And what makes this genuinely dangerous to every company currently selling you winter heat is not complicated. It is one idea. Once you understand thermal storage, once you actually grasp what it means to hold heat in dense material and release it on your own schedule, you stop renting comfort 1 month at a time. You stop being a customer of necessity. You start being someone who owns their warmth rather than subscribing to it. Today, I'm going to show you a system you can build yourself for a few $100s using gravel, sand, brick, or stone. Materials available at any hardware store or landscape supplier, or sitting unused in a field behind someone's barn. Once it is charged with heat, it can hold that warmth for days without any fuel burning, without any electricity running, without any ongoing cost of any kind. Stay with me, because by the end of this, you will understand why people who live far from cities and far from gas lines have quietly used versions of this principle for generations, and why everyone else kept paying bills they did not have to pay. Before we build anything, let us clear up the biggest misunderstanding that follows this topic everywhere it appears, because the misunderstanding is what makes people dismiss it before they understand it. This is not magic. It is not free energy. Nobody is violating thermodynamics or extracting heat from nothing. This is stored energy, the same way a well-made thermos stores hot coffee and keeps it drinkable 4 hours after you poured it, the same way a cast iron skillet stays warm on a cold stovetop long after the burner is off, warm enough to finish cooking what you started. The same way a stone wall facing south in a Mediterranean courtyard absorbs heat all afternoon and radiates it back into the space through the evening, keeping the courtyard comfortable hours after the sun is gone. Dense materials absorb heat and release it slowly over time. Scientists call this property thermal mass, and it is one of the most useful physical properties available to anyone trying to manage temperature without ongoing fuel consumption. Stone, brick, sand, dry concrete, and compacted dry soil all share one critical trait. They can accept large quantities of heat energy without being damaged, without changing state, without requiring any special treatment. And then they give that energy back gradually and steadily as the surrounding temperature drops below their stored temperature. That means if you heat a large enough mass during the day, you have heat available that evening without burning anything. If you charge it hard on a Saturday when your wood stove is running hot, you may feel meaningful warmth from that stored energy on Monday morning without adding a single piece of wood after Sunday. The energy is not created. It is not multiplied. It is shifted in time. It is captured when it is available and released when it is needed. And once you genuinely understand that distinction, once it moves from an abstract idea to something you can feel the implications of, winter changes. The economics of staying warm change. Your relationship to fuel, to utility companies, to the anxiety of watching a tank gauge drop changes entirely. Imagine a steel drum filled with dry gravel and coarse masonry sand, heavy and dense, packed tightly enough that the thermal mass per cubic foot is maximized. Through the center of that packed fill runs a coil of black steel pipe, wound from bottom to top in a spiral that brings as much pipe surface area as possible into direct contact with the surrounding stone. Outside the drum is thick insulation, enough to slow heat loss to a rate measured in days rather than hours. Heat enters the system through that pipe coil from whatever source you are using, a loop from a wood stove, a solar thermal panel on the roof, an electric heating element running during off-peak hours when electricity rates are low. That hot fluid, or steam, moving through the pipe, transfers thermal energy into the gravel mass surrounding it. The stones warm up slowly, deeply, evenly, absorbing heat without any of the violent temperature spikes that would damage lighter materials. Then later, hours or days later, when the fire has gone cold or the sun is set or the cheap electricity window is closed, you run cooler air or water back through the same coil. The stored heat in the stone, still sitting there patiently, still holding the energy you put in earlier, transfers back into the circulating fluid. That warmed fluid carries the heat to wherever you need it. No roaring furnace needed, no constant feed of fuel, no noise, no combustion, no maintenance required in the moment, just yesterday's heat held in stone, paying today's bill at whatever pace you need it. Here is the version most people can actually build this weekend with a limited budget and without specialized skills or tools. Start with one used 55-gallon steel drum in genuinely good condition, not heavily rusted, not structurally compromised, without any coating or residue from previous contents that would off-gas or burn when heated. Avoid plastic containers entirely, not because plastic cannot hold heat, but because the temperatures you are working with will degrade it over time and create problems you do not want inside an insulated heating system. Steel matters because it handles repeated thermal cycling, expanding and contracting with temperature changes without cracking, and it supports the considerable weight of the stone fill inside it without buckling. A filled 55-gallon drum packed with gravel and sand is heavy. The container needs to be structurally equal to that load across years of use. Fill the drum with dry gravel mixed with coarse masonry sand, not wet dirt from the garden, not river mud or clay-heavy soil. Dry, clean, granular material that transfers heat efficiently through direct contact between particles, does not create steam problems when it gets hot. The mixture of coarse gravel and sand fills the void spaces between larger stones and increases the total thermal mass packed into the volume of the drum, which directly increases how much heat the system can store per charge. Into that fill, before you seal the drum, install 25 to 40 feet of half-inch or 3/4-inch black steel pipe arranged in a spiral coil running from the bottom of the drum to near the top, maximizing the surface area of pipe in contact with the surrounding stone. Leave 2 pipe ends accessible through the lid or through the side wall near the top and bottom. One becomes your hot inlet, where heated fluid enters the system during charging. The other becomes your outlet, where fluid exits after giving up its heat to the stone. Those 2 connections are the entire interface between your thermal battery and whatever heat source and heat delivery system you connect to it. Next comes the element that separates a useful thermal battery from a warm barrel that cools back to room temperature by morning and accomplishes nothing. Insulation, not a thin wrap, not fiberglass. Bats designed for wall cavities, real, serious thermal insulation applied generously enough that the rate of heat loss from the drum is reduced to something that allows useful storage over multiple days rather than a few hours. 4 inches of mineral wool, ceramic fiber blanket, or rigid high-temperature foam insulation applied around the entire exterior of the drum, including the top and critically the bottom, creates a barrier that slows heat loss dramatically. Cover the insulation layer with sheet metal or exterior-grade plywood to protect it from physical damage and moisture. Pay particular attention to the bottom. Concrete slab floors are thermal sinks. They will draw heat out of an uninsulated drum sitting directly on them faster than most people realize, and all the insulation on the sides means nothing if the bottom is losing energy downward into a slab that extends to the cold ground outside. Set the insulated drum on wooden pallets, on rigid foam board, on concrete pavers with insulation beneath them, on anything that breaks the direct thermal contact between the drum base and the slab below. Heat saved through careful insulation is heat you do not have to put in twice. Every improvement to the insulation envelope of the system multiplies the value of every charge you put into it. Now the charging methods, because this is where people tend to overcomplicate the concept until it stops feeling buildable and becomes a theoretical exercise. Method 1 is wood heat integration. If you already run a wood stove during winter, you have a heat source that routinely produces more thermal energy than a room can absorb efficiently, especially during the peak burning period when a stove is running hot. A simple heat exchanger, a coil of pipe running through or near the stove body or around the flue pipe, captures some of that heat into circulating water before it goes up the chimney and out of the house. That hot water moves through insulated tubing to your thermal battery, passes through the coil inside the gravel mass, transfers its heat to the stone, and returns cooler to be reheated. You burn one good hot fire in the evening. You charge the mass. The fire dies down or goes out overnight. The stored heat in the stone continues radiating into the space slowly for the next 12 to 24 hours. The wood you burned is gone, but the heat it produced is not. It is sitting in the stone, waiting. Method 2 is solar thermal collection. A simple flat plate solar collector, a dark surface under glass or clear polycarbonate, mounted at the correct angle on a south-facing roof or wall, heats water during daylight hours, and sends it through the coil in your thermal battery. Even winter sun at low angles in northern latitudes carries meaningful energy, enough to make a real contribution to the stored heat in your system on a clear day. The water heats during the day, charges the stone, and the stone releases that warmth through the evening and into the following morning. The sun is not burning anything. There is no fuel. The collection happens passively, automatically, every clear day, adding to a thermal reserve that accumulates over multiple charging cycles. Method 3 is off-peak electricity. Rural electricity customers in many regions have access to time-of-use rates that make electricity significantly cheaper during nighttime hours when grid demand is low. A simple resistance heating element installed inside the drum or in the fluid circuit, controlled by a basic timer set to run during the cheap rate window, heats the thermal mass during those hours. The stored heat is then released during the expensive daytime period when you actually need warmth, effectively shifting your energy consumption from high rate to low rate periods and reducing your electricity bill even while maintaining or improving your comfort. 3 completely different energy sources. The same principle in every case. Capture heat when it is cheap, abundant, or otherwise available. Store it in dense material. Use it when it is valuable, when you need it, on your own schedule. What kind of honest performance can you actually expect from a system like this, built at the scale most people are likely to start with? Let us be direct about this, because unrealistic expectations destroy good ideas faster than technical failure does. One insulated 55-gallon drum filled with gravel and sand is not going to heat a large, drafty farmhouse through a week of hard Canadian winter by itself. It is not a replacement for a full central heating system in a poorly insulated house with high heat loss. If your building envelope is leaking heat through gaps in thin walls and single-pane windows, no thermal storage system will overcome that deficit cleanly. But a single well-built drum system can absolutely and reliably warm a workshop or garage through a cold night after one charging session. It can maintain a greenhouse above freezing through a week of below zero nights when charged regularly. It can keep a small, well-insulated cabin or off-grid sleeping cabin comfortable with a heat input that costs almost nothing if it comes from solar or from wood that would have been burned anyway. It can reduce furnace runtime meaningfully in a larger house by handling the overnight load that accounts for a significant portion of monthly fuel consumption. It can carry warmth through a day when you're not home to run the stove and would otherwise return to a cold house. 2 or 3 linked drums, properly insulated, charged through a good solar thermal system or an efficient wood heat loop, can become the primary heating backbone of an off-grid small home in moderate winter climates. A larger, purpose-built insulated tank, using the same principle at greater volume, can become the central heating system for an off-grid home that captures solar heat in summer and releases it months later in winter, a concept called seasonal thermal energy storage that is actively used in district heating systems in Denmark and Sweden at scales large enough to heat entire neighborhoods. The physics of what you build in your shed is identical to the physics those systems operate on. The difference is only scale. There's a critical piece that most homeowners leave out of the analysis when they evaluate heating systems and then wonder why modest heat sources seem to underperform. The building itself is the system. A thermal battery, no matter how well charged, is fighting a losing battle if the building it is trying to heat is losing energy faster than any reasonable heat source can replace it. Cold air infiltrating through attic penetrations and bypasses. Heat escaping through uninsulated rim joists at the foundation. Windows with failed seals or no thermal break. Doors that let cold air in at the bottom every time they close. Attic insulation that has settled or been disturbed or was never adequate to begin with. Every one of these is a hole in the bucket. You can pour heat in at the top as fast as you like, but if the bucket leaks, you spend all your time and fuel just keeping up with the loss rather than building up stored comfort. Seal attic penetrations with spray foam and rigid board. Add weather stripping to every door that shows daylight around its frame. Install thermal curtains on north-facing windows and close them at sunset. Insulate exposed pipes and crawl spaces. Add a layer of rigid foam to a cold basement wall. Each of these improvements, measured individually, seems modest. Combined, they can cut the heat demand of a house by a third or more. And when you cut heat demand by a third, the modest output of a thermal battery system suddenly looks impressive rather than marginal. The smartest heating upgrade available to most homeowners is not a better furnace or a more efficient heat source. It is stopping the losses that make every heat source work harder than it should have to. There is deep history behind this principle, and the history matters not as nostalgia, but as evidence. Before gas furnaces, before oil boilers, before utility companies existed to sell warmth by the unit, people in cold climates were solving the same problem with the same fundamental tool: dense material that holds heat. In Scandinavia, the masonry stove, known in different forms as the Finnish contraflow stove, the Swedish kakelugn, and the Norwegian kamin oven, was a fixture of domestic architecture for centuries. Built from brick and soapstone and ceramic tile, these stoves were fired once or twice a day for a relatively short burning period, but their massive thermal mass stored so much heat from that intense fire that a single family-sized stove could heat a room continuously for 12 to 24 hours on one charge of wood. The fire was the charging event, the stone was the battery, the room was the beneficiary, warm all night from a fire that had gone out hours earlier. In Russia and Eastern Europe, The Russian masonry heater, the pech, was the central architectural element of traditional homes, sometimes occupying the corner of a main room with dimensions large enough that people slept on top of it, using the stored body heat of the stove the way we use electric blankets today. In Korea, the Ondol system ran hot air or hot water through channels under stone floors, turning the entire floor surface into a radiant thermal mass that warmed rooms from below with a gentle, even heat that is widely considered one of the most comfortable forms of indoor warmth ever devised. Roman hypocaust systems under public baths and wealthy homes moved hot air beneath raised floors and through hollow wall tiles, using the structural mass of the building itself as a thermal storage and distribution medium. All of these systems, developed independently across thousands of years and thousands of miles of separation, arrived at the same operating principle through direct observation and iterative refinement. Burn hot for a short, concentrated period. Store the heat in dense material. Release it slowly over many hours. Modern utility infrastructure made people forget that this approach had ever existed, replacing the masonry stove with a furnace that burns continuously because continuous burning requires continuous fuel purchase. But the physics did not go anywhere. The stone never stopped holding heat. The principle is exactly as effective today as it was in a medieval Swedish farmhouse, only the awareness of it has changed. Maintenance on a thermal storage system is almost laughably simple compared to every modern HVAC system you have ever owned or rented space in a building that contains. There are no compressors cycling on and off under pressure, no refrigerant lines that develop slow leaks and gradually reduce efficiency until the system fails completely on the most inconvenient possible day. No circuit boards, no pressure sensors, no ignition assemblies, no draft inducer motors, no flame sensors that develop carbon deposits and start causing intermittent failures, no filter that needs monthly replacement, no annual service contract required to keep the warranty valid. The practical maintenance of a well-built stone thermal battery consists of checking the pipe fittings at the inlet and outlet once per season to ensure no leaks have developed, inspecting the insulation layer for moisture infiltration or pest damage that would reduce its effectiveness, and confirming that any circulation pump used to move fluid through the system is still operating quietly without unusual vibration or noise. That is approximately the complete list. The stones inside the drum do not degrade. They do not oxidize or corrode or wear out. Dry gravel that has been absorbing and releasing heat for 10 years is functionally identical to dry gravel that has been doing it for 1 year. The sand does not expire. The pipe, if it is black steel rather than copper or plastic, will outlast the building it sits in. The insulation, if protected from moisture and physical damage, maintains its properties for decades. The entire system is built from materials whose individual lifespans are measured in generations, assembled in a way that has no failure-prone mechanisms. The boringness of the maintenance schedule is a feature, not a limitation. It is what makes the system genuinely practical for people who do not want to spend their winters managing equipment. There is something that is difficult to quantify, but that people who have built and lived with these systems consistently describe, and it deserves to be named directly because it is part of what makes the investment worthwhile beyond the financial arithmetic. There is a qualitative difference in warmth that comes from thermal mass compared to warmth that comes from forced air or baseboard electric heat. Radiant warmth from a heated stone mass heats objects and surfaces in a room, not just the air. It heats the walls, the floor, the furniture, the structure itself. When the air temperature in a room drops slightly, you do not immediately feel cold because the surfaces surrounding you are still radiating warmth. The sensation is enveloping in a way that blown air never achieves. People who have experienced this consistently describe it as the most comfortable form of indoor heat they have encountered. And layered on top of that physical quality is something psychological. Waking up at 5 in the morning when the outside temperature is below zero and feeling the room still warm from heat you stored the previous afternoon without any fuel burning, without any meter turning, without any bill accumulating for the warmth you are experiencing produces a specific kind of satisfaction that is genuinely difficult to explain to someone who has only ever experienced purchased heat. It is the feeling of sufficiency, of having provided for yourself in a fundamental way, of comfort that you own rather than rent. That feeling is not nothing. For a great many people who build these systems, it turns out to be worth at least as much as the money saved. If you are starting from scratch this weekend with a limited budget and no prior experience building anything like this, here is the honest, practical path forward. Find one used steel drum in good condition, available from agricultural suppliers, restaurant equipment resellers, industrial surplus dealers, or often for free from businesses that receive products in steel drums and have no use for the empty containers. Buy dry gravel and coarse masonry sand from any landscape or construction supplier. Buy 25 to 40 feet of black steel pipe in the appropriate diameter and have it bent into a coil, or bend it yourself if you have access to a pipe bender, which many hardware stores will do on site. Buy 4 inches of mineral wool or ceramic fiber insulation, enough to cover the drum and lid and bottom with a complete thermal envelope. Connect the coil, inlet, and outlet to your existing wood stove loop if you have one, or install a simple resistance heating element and a timer if electric off-peak rates are available to you, or build a basic flat-plate solar thermal collector from black pipe under polycarbonate sheeting if solar exposure is your best available resource. Set the completed insulated system in the space you want to heat. Charge it with one full heating session. Come back in the morning and put your hand near the outlet vent and feel whether useful warmth is still coming from stored energy. Measure how long the stored heat lasts under your specific conditions and in your specific space. Learn the timing. Learn what charging intensity produces what duration of output. Then, once you have verified performance at one drum, consider whether your situation justifies adding a second drum, a third, a larger custom-built tank. Let the results of the small version guide the design of the larger one. That is how practical systems get built by practical people, not from a blueprint handed to them by someone who has never lived in their climate or their building. From their own observations of a small working version that they understand completely because they built it themselves. Because once you stop thinking that heat must be purchased in real time from a company that charges more for it, the more desperately you need it, everything about how you relate to winter changes. Heat can be stored. Heat can be moved through time. Heat can be captured on a warm afternoon and held in stone until a cold morning 3 days later calls for it. Heat can wait for you, patiently, in a drum full of gravel in your shed, until you need what is inside it. That single idea, stored thermal energy, energy shifted in time rather than consumed in the moment it is produced, has been quietly keeping intelligent, observant people warm for centuries in some of the coldest places humans have chosen to live. The utility companies did not invent a better way to stay warm. They invented a more profitable way to sell it. The stone was always there. The physics was always there. And it is still there, waiting in a drum full of gravel for the weekend you decide to use it.